Hello guys, today I'll be talking about IPv4 classful addressing. IPv4, okay, what is IPv4 classful addressing? It is actually about the architecture used in the internet from 1981 until the classless domain came out in 1993, I guess. Yeah, okay, yeah, 1993. So it basically consists of 5 classes, which is class A, B, C, D, and E. Okay, this, for example, for class D, it is for usually for multicast purposes, and for class E, usually used for reserved and experimental purposes. Okay, moving on, we'll be discussing about the topics now. Okay, so we'll be talking about classes, blocks, structure of IPv4, subnetting, and supernetting. Okay, as you can see, okay, let's start off with classes of address. Okay, as you can see, it starts from 0, 1, 0, 1, 1, 0, and so on. Okay, it's going in an ascending order, and it always consists of 1 and 0s. Just remember that it always consists of 1s and 0s, which is called binary notation. Then, okay, now we're talking about dotted decimal notation. As you can see, from class A, it starts from 0 to 127. And from class C, it ends at 255. Why? Because that's the maximum of the IP address that can take in. So this is basically we call dotted decimal notation. So moving on to classes and blocks. Moving on to classes and blocks. The classful addressing wastes a large part of address space. As you can see, these are all the classes, which is, as I said before, class A, B, C, D, and E. Okay, so now don't mind the blocks and the block size, because these are not always the important part. These are the important part. So as you can see, class A, B, and C are the unicasts. Unicasts are not usually very important, but mainly people will be using the class D because this is multicast, and if it fails, it always goes to reserve, as it is class E. So moving on, we'll be talking about. Okay, now we'll be talking about structured IPv4 address. Okay, it consists of net ID and host ID. So these are the actual binary and dotted decimal notations. So as you can see, it's going ascending, 1 1 1 1 and 0 0 0 blah blah blah. So like it goes from like, it's like one group of ones, then two groups of ones, three groups of ones, then same goes to dotted notation, and it always adds on by 8, which is the CIDR. So moving on is mask. What is mask? Mask is a 32-bit number of contiguous ones followed by contiguous zeros. It is also used to help the host and the net ID. Now we'll be talking about the subnetting. It divides a large address block into smaller subgroups, and it's also a flexible net mask. It exhausted class A and B, and it's a huge demand for class B address space, and it also used to combine several contiguous address spaces into a larger single address space. Okay.
Hi guys, I'm Jonathan. Today I'm going to explain to you about routing process. Before we start the routing process, first we have to go through path determination. This basically enables the router to compare the destination address to the available routes in the routing table. This also helps to select the best possible path for routing. Before we start the path determination, first we have to determine whether routing is required. To do this, the network layer uses a network mask that has 1 for each bit in the network portion of local address, and also 0 in the host portion bits. The next process is routing. Routing is basically a process of finding the most efficient path from one device to another. This means sending packets through the network with the intention of getting each one to its proposed destination. A router is basically a process where packet forwarding. A router uses packet forwarding to send a packet. If the packet cannot be delivered locally to its final destination, then the router uses its routing tables to find the best routes towards the destination. The router has basically two key functions. First is maintain routing table. It makes sure that the other routers know of changes in the network topology. Secondly, when packets arrive at an interface, the router must use the routing table to determine where to send the packets. It switches them to appropriate interface. So here we have an example of the routing process. You can see the IP address of 172.16.2.0 matches the destination IP address of 172.16.2.2. This means the packet can be sent to the destination IP address. Next is the routing table. The routing table has basically four main elements: the protocol type, the destination and next hop association, routing matrix, and outbound interface. The protocol type is the type of routing protocol that created the routing table entry. Destination is basically a process where it tells a router that a particular destination is either directly connected to the router or that it can be reached via another router called the next hop on the way to its final destination. The routing metrics are used to determine a router's desirability. Finally, the outbound interface is the data must be sent out to reach the final destination. This is an example of the routing tables. So when conducting the routing process, we basically look at the network address like 1.92.168.11.0. We also look at the hop, which is the next destination. The bits of 0 and 1 are looked at. There are two types of routing processes: static routes and dynamic routes. Static routes. Static routes are routes learned by the router when an administrator manually establishes the route. The administrator must manually update the static route entry whenever an internet network topology requires an update, such as during a link failure. The second route is dynamic routes. Dynamic routes automatically learned by the router after an administration configures a routing protocol that helps determine the routes. So basically, unlike static routes, as soon as the network administrator enables dynamic routing, the route knowledge is automatically updated by a routing process whenever a new topology information is received from routes within the internetwork. This is an example of dynamic routing. The next part of the routing process is routed protocol against routing protocol. So routing protocols is done to determine the path that routed protocols follow to their destinations. So examples of routed protocol are IP and IPX. For routing protocol, the examples are RIP, IGRP, and OSPF. Routing protocol are used between routers to maintain tables, while routed protocol are used between routers to direct user traffic. Routing protocols are used to exchange routing tables and share routing information as well. It basically provides processes for sharing route information. It also allows routers to communicate with each other routers to update and maintain the routing tables through the process of transmission of routing updates. As I said before, the examples are RIP, Routing Information Protocol, IGRP, Interior Gateway Routing Protocol, EIGRP, which is Enhanced Interior Gateway Routing Protocol, and OSPF, Open Shortest Path First. For routed protocols, it is a protocol that transfers data from one host to another across a router. There are routed or routable protocols. It basically includes any network protocol suite that provides enough information in its network layer address. It allows a router to forward it to the next device and ultimately to its destination. Examples of routed protocol are IP, IPX, which is Internet Network Packet Exchange, and AppleTalk.
Okay guys, my name is Srikanth. I'm going to be talking about network address translation, NET. Well, network address translation is used to connect a network to the internet using a private address, which requiring the translation of the private address to the public address. For example, a company is allowed by network address translation to use few registered IP address instead of an entire network. Hosts inside the company network is typically used private IP addresses. Network address translation can also translate from public address to private address, so it goes both ways, private to public, public to private. The most important thing in network address translation is we must know to identify the local address and the global address. So right here we have private network, we have public network. So most of the time the network we will have this side, the private network, and the public network over this side. So there will be data, the data packet will be transferred from here, from this PC or web server or what, be transferred to here, the internet user. So for example, right now we have the IP address over here 192.168.0.1, which needed to translate this thing from here to here. So this thing will move all the way to the router, and the router will realize that here the IP address and here it's different. Here is 192.168.0.1, whereas here is 171.68.1.1. So the router will change the IP address accordingly to the public network IP address. For example, right now is 192.168.0.1. It will change to maybe 170.168.0.1, where when it's 170.168.0.1, it will be like possible to be translated from private network to public network. So as this happens, then the data packet is managed to be transferred to the internet user. And if let's just say the data packet is to transfer back to the PC, so we are having the IP address that has been changed just now, which is 170.68.1. It has to be transferred back, to change back to the original IP address, which is 192.168.0.1. It should be changed back, should be translated back to the original IP address. It's because that so that it can be transferred, can be translated back. And so that's how NAT works actually. NAT, it will divide in the network into private network and public network. So type of addresses. So we should know that inside local network area, where the private IP address is being translated into public IP addresses. We must know this. And next off is inside global IP address. Inside the global network, where the public IP address is the public IP address and the private IP address is being translated into. So that's the inside the global is where the process where the private IP address is being translated into the public IP address. Outside global will be those things that is happening outside the public IP address. So there's two type of network address translations. So one type, it will be the static network address translation, and another type will be dynamic network address translation. So the static network address translation is useful when a network device inside a private network needs to be accessible from the internet. Dynamic network address translation can be defined as mapping of a private IP address to a public IP address from a group of public IP address called the network address translation pool. It's been called as the network address translation pool. So this is how you configure the static network address translation actually. So for over here we have one example here. So this side, it will be the local addresses inside the network, and this side we will be having the inside interface, the outside interface, and here is the NAT translation, the NAT translation, and over here is outside global addresses. And I think that's all from network address translation from me.
Hi, my name is Vickneswaran Arumugam. I would like to talk about IPv4 classless addressing. Firstly, we should know about subnetting. Subnetting and supernetting in classes addressing did not really solve the address repression problem. With the growth of the internet, it was clear that the larger address space was needed as a long-term solution. Although the long-range solution has been devised and is called IPv6, a short-term solution was also device to use the same address space but to change the distribution of address to provide a fair each organization. A short-term solution still uses IPv4 addresses, but is also called classless addressing and also known as supernetting too. Combine several addresses blocks to create larger address range, or also known as supernet. Instead of using a single net for multiple subnet, it allows a subnet addresses to span multiple classless addressing to overcome the depletion of address space. There is also a restriction. The restrictions are the address in a block must be constant. The number of the addresses in a block must be power of 2. The first address must be evenly divisible by the number of addresses. Next, we like to talk about mask. Mask consists of n consecutive and ones followed by zeros. N can be any number between 0 until 32. And also there's a tip in IPv4 addressing. A block of address can be defined as x, y, z and t and also n, in which x, y, z t defines of the address, one of the addresses, and the \n defines the mask. The first address in the block can be found by the setting rightmost 32 bits to zeros. The last address in the block can be found by setting the rightmost 32 bits to ones. The number of the addresses in the block can be found using the formula 32 ones. Next, address block assigning. You must choose the address randomly so that the routers outside the supernet state each are blocked separately. Each router has n entries in its router table and the infinite number of blocks, therefore increase the size of the routing table tremendously. Choose address blocks based on a set of rules so that each router has only one entry in the routing table. It is also required by CDI, also known as classless inter-domain routing. Infinite number of blocks such as a power of 2, 1, 2, 4, 8 and so on. The size of each block is power of 2. The blocks are contained in the space address, no gaps between the blocks. The size of supernet is a multiple of 2 and the first address can be evenly divisible by supernet size. Blocks also can be defined in different addressing schemes blocks such as first address and last address. Meanwhile, classful address has only one block, unlike a classless address because clusters full address also have a default mask always known. The first address can be define the block. Besides supernetting is the first address for the supernet and the supermask. IP address and supermask are the first network address. There is also a variable length block in addressing. Suffix varying part of the address range or suffix length can be maximized up until 32. Finally, subnetting. Subnetting has different classes which increase the supernet prefix length to define the subnet prefix length. Subnet address ranges are firstly 130 up to 130. There are also 4 phases of subnet. Under the category of subnetting, reserved CIDR blocks are one of the things. Private addresses and unroutable addresses used with private networks such as Wi-Fi and for some encryption purposes, which was never assigned to network in the global internet. Router in the global internet knows they are reserved addresses and can detect if a packet is sent to reserved address accidentally reaches the internet. These are the prefix for first address and last address.